Aloha and welcome to my talk on offensive malware analysis. So my name is Patrick. I've worked for a variety of acronym places. I'm currently the Chief Security Researcher at SYNAC. So briefly, SYNAC does crowdsourced vulnerability discovery with vetted security researchers. I'd love to chat more about this after the talk or check out synac.com. Okay, so today we're going to be talking about analyzing an intriguing piece of Mac malware named FruitFly. But the way we're going to do this analysis is somewhat different. So we're going to start with a brief overview of the malware. And this brief triage or goal is basically so that we have enough of an understanding so that we can build a custom command and control server. We're then going to talk about some tools and techniques that allow us to monitor the malware while we task it. We're then going to jump into building the custom command and control server before talking about tasking it, which will allow us to understand its capabilities by just asking the right questions. And then finally, we'll talk about what happened when I put this custom command and control server on the internet. So the goal here is to comprehensively analyze FruitFly, but do so in a more efficient way. So traditional methods of malware analysis are usually done with debuggers or disassemblies. And yeah, these techniques work, but they're rather slow. Now, I didn't have access to a command and control server, but I figured if I wrote my own, I'd then be able to task the malware and then observe its responses. This process then, I assumed, would allow me to coerce the malware to reveal its capabilities simply by asking the right questions. And I figured this technique would be a lot faster. And an upside is, if in some way you can take over the domain or the address that the malware is beaconing to, perhaps you can hijack all the attacker's pieces of malware. So as I mentioned, the target of this analysis is a Mac malware specimen named FruitFly. Now, before we build our custom command and control server, we need to perform a basic triage so we can answer two questions. And that is, what address does the malware try to connect to for its command and control server? And then also, what protocol does it speak? Because this will allow us then to create a custom command and control server that is compatible with the malware. So FruitFly was discovered in January by my friend Thomas Reed at Malwarebytes, and he blogged about it, giving a great overview of the capabilities of the malware. He also talked about various components and its method of persistence. It's a fairly standard backdoor, but it's very feature complete and has some unusual features that are more surveillance related. For example, can turn on the webcam and even interact with the mouse and keyboard. Now, we don't know the infection vector, but if we had to guess, maybe a malicious email document, a Trojan application, an infected website. However, we never found an installer, so perhaps there's a different infection mechanism altogether. So today we're going to be talking about variant B. Variant B was submitted to VirusTotal a few weeks after variant A. And even though variant A at the time was being detected by antivirus engines, variant B originally was not. Now, it was submitted to VirusTotal with the name of FPS odd. I believe that's to mimic a common Flash player component. And like variant A, the main malware component was an obfuscated Perl script. Perl, kind of interesting. So, as I mentioned, our goal is to build a custom command and control server. And so we need to know the address that the malware tries to connect out to, so we can place our command and control server there, at least in a lab setup. And then also understand its protocol so that we can communicate with the malware. So let's now briefly talk about triaging the script to get this information. So the first thing we can do is we can beautify the script. It's obfuscated, minimized Perl, so by beautifying it, variable names and subroutines are still obfuscated or meaningless, but at least it's formatted more better. So we can see, if we looked at the formatted script, it starts with a variety of imports, some subroutines, and then is followed by the main logic. So briefly, let's look at these subroutines. On the slide, I created a table describing all the subroutines and their rather meaningless names. Now, these subroutines are not the core logic of the malware, but they're helper functions that can provide a lot of insight into the protocol of the malware. So for example, we have subroutine G. G is used to send data to the command and control server. So for example, if we see a command invoking the subroutine G, it'll probably show us at least how many bytes it's going to send back to our command and control server, and then we can extend our command and control server to handle that command response. Somewhat similarly, the subroutine J receives some number of bytes from the command and control server. So again, if a command invokes, say, J9, we know that it expects 9 additional bytes for that command. So again, we can then customize our command control server to make sure for that command we pass 9 additional bytes, even if originally we don't know what those 9 bytes should be. So after the subroutines, the malware decodes some strings, which turn out to be the addresses of the backup and primary command and control servers. One way to debug these, or rather decode these, is just to debug and step over the subroutine that performs the string decoding. So we can do that by executing Perl-D. This will run the malware in a Perl debugging session. Now we're not going to debug the entire malware, because that would take way too long, but we can simply step over this routine and then print out the values. And very easily we can see that they're the IP addresses and the URLs of the primary command control servers, albeit reversed. And then on the slide, there's some code that we can see uses these addresses to connect to the attacker's command and control server. Now after decoding the addresses of the primary and backup command and control servers, the malware processes some command line arguments, hides its process, and then unpacks some binary data. So if we look at the code that processes the command line arguments, we can see it looks for a port or an address : port of a custom or command and control server. This is awesome because this means we can now specify via the command line the address of our own command and control server for tasking and analysis purposes. This definitely facilitates analysis. In terms of process hiding, it just sets argv0 to Java. This is really not a sophisticated technique, but we can see that at least terminal and tools such as PS are fooled. So if you do a PS listing, you'll actually see a process named Java instead of the malicious Perl script executing. And what about that encoded data? That turns out to be an embedded mock-O binary that we will talk about shortly. Finally, we get to the main processing loop, which does two things. It checks in with the command and control server, sending version of the malware, host name, and username. And then it invokes the J subroutine to receive 1 additional byte, which it then processes via a massive if else if loop. And what this is all doing is checking in with the command and control server and then getting a numeric command to execute. And then once it executes that command, it sends the response back to the server and just repeats forever. Okay, so we know the address of the command control servers. More importantly, we actually know that via the command line we can specify our own. We also understand the basic protocol. Now, before we start building the custom command and control server, let's talk about being able to passively monitor the malware. This is very important because even if we can task the malware, if we have no way to observe what it's doing, the tasking is kind of pointless. Imagine some command, say 6, returns a 0 or 1. Like, what does that even mean? So what do we want to monitor? Well, basically as much as possible. Because a given command might create files, write files, read from files, it might spawn processes, it might execute shell commands, it might interact with the mouse and the keyboard, and even send back some interesting data via the network. So we should monitor for all these events so that we can again understand the malware's capabilities just via tasking. So let's take a closer look at each of these. Network monitoring, pretty easy to do because there's built-in tools and capabilities already. So top of the slide, you can see that when we run TCP dump, we can see the malware connecting out, trying to resolve its command and control server. Again, this is another way where you could determine the address of the CNC server. Now we'll talk about tasking more, but on the bottom of the slide, we can see a network capture from Wireshark when the malware is responding to command number 13. Now originally we have no idea what command number 13 does, but if we look at the network capture, we can see this command returns the location where the malware is installed. Next up, file monitoring. Again, pretty simple. There's a built-in utility fsusage on Mac OS. You can execute this as root and it will monitor for file O events. This is important because a variety of commands will cause the malware to drop its embedded mock-O binary. And we can see via the file monitor that this is saved to /temp/client. So then we can grab that and analyze that. We actually don't have to do much analysis because again, we're just going to task the malware and see what it does. Next is process monitoring. Now, unfortunately, as far as I know, there was no open source free user mode process monitoring utility for Mac OS, so I decided to write my own. What it does is it interfaces with the audit subsystem. It's really actually easy to do. Once you link the library, you can see code on the slide. It's about 5 or 6 lines of code. Basically, you link in the library, instantiate a process monitor object, and then pass it a block that will be automatically executed by the library every time a process starts. So for example, via command number 11, we can see that when the process monitor runs, it sees the malware executing the pwd command to get the current working directory. I also wanted a mouse and keyboard sniffer. I found some old proof of concept code that would intercept and modify these events. So I updated that for Mac OS and turned it into a pure sniffer. So it'll capture both mouse and keyboard events. So now you can see if we type or move the mouse, the sniffer will detect these events, which again will be very useful via the tasking of our malware. All right, on to building our custom command and control server. Recall, we can specify the address of the command and control server via the command line. And we also understand the basic protocol. Malware checks in, sends some client information, and then expects a single byte command to execute. So we can start by just writing some Python code that accepts a connection. If we do this, run this, the top you can see we execute the malware. The command line, we provide it the address of our command and control server, and the malware connects. Okay, not that exciting, but baby steps. So what does the malware do when it originally connects? What does it check in? So as we mentioned, it sends some data, but what is the format of this? So we can briefly look at the malicious Perl script, and we can see it packing and then sending back some strings via the G subroutine. And it sends things like version name, host name, and username. So what we can do is we can then extend our custom command and control server to process and parse this data so that whenever a piece of malware connects, we can dump this to standard out or save this to a file. Now, the meat of the custom command and control server is obviously tasking and handling command responses. Turns out there's about 25 or so commands. Some of these have subcommands, bringing the total to about 50. So what I did was I built a custom command and control server to support all of these. Now, I originally didn't know what all these commands would actually do. So what I did for each command is I would triage the command to look for any command-specific protocol. For example, does that command expect additional bytes? And also, what is the format of the response? Then I still wouldn't know what the command actually did, but I would task and observe the response. So here's a very simple example, command number 11. We can see that it expects no additional data, but then responds via the G subroutine, sending back a single byte and then a variable length string. So what we can do is we can extend our custom command and control server, and then we can see when we support this command that it's the malware returning its current working directory. Okay, so now we task. Again, we've got our monitoring capabilities. We're monitoring file system, network traffic, mouse, keyboard, processes, and also our custom command and control server. Now, unfortunately, we don't have time to go through all the commands, but let's look at how we can expose some of the more interesting ones just via tasking. And again, when I started this tasking, I had no idea what these commands would actually do. So let's start with command number 2. If we look at the Perl script to briefly triage this command, we can see it invokes J to read an additional byte from the command and control server, invokes the V subroutine, which drops and executes that embedded mock-O binary, and then invokes the G subroutine to send some response back to the server. So now we understand the format of the protocol, but again, we have no idea what this command actually does. So if we send the malware command number 2, and for that second byte just execute 0, or rather pass a 0, we can see, yes, the file monitor detects that the malware is dropping this embedded mock-O binary, and then the process monitor shows that it is then being executed. Then via the network capture, we can see it sends back some large amount of data, 1 meg plus. So what we can do is we can extend our custom command server so that for command number 2, we know it's going to send us back a large chunk of data and write that out to the file system. We can then dump that file in a hex editor or run the file command, and we can see it's actually a PNG image. And then once we open that image, we can see that it's a screen capture. So now we know command number 2 is the screen capture command. Again, we just figured this out via tasking. Now, remember this command, though, takes a second additional byte. Again, I had no idea what this was. I passed it a 0, and it returned the screenshot. But we have the ability to task the malware. So we can just send various values for this second byte and see what the malware does, how it responds. This is really the power of the custom command and control server and tasking. We don't have to do any additional reverse engineering. So we can see on the slide a table of contents, basically the results, and we can see that the second byte influences both the type and quality of the screen capture. For example, you pass it a 1, it sends back a low resolution black and white PNG, while a 10 will send back a low res JPEG image. All right, on to command number 8. Again, we briefly first triage this command. We see it expects additional 9 bytes. Again, it then drops and execs that embedded binary, passing in those 9 bytes. And for its response, it only sends back 1 byte, which is either a 0 or a 1. So unlike the screen capture command, looking at the response, we have no idea what this command does. Like, what does a 0 mean? What does a 1? What did the malware even do? But when we task, passing in 0, 1, 2, 3, 4, 5, 6 for those additional 9 bytes, we see the mouse sniffer registers an event and a move to the XY coordinates we specify. So if you watch very closely on the screen, you're going to see me tasking the malware, and ooh, the mouse moved. Amazing, right? Okay, so what about that second byte? Again, we know the last 8 bytes are the XY coordinates, but we don't know what that initial byte is. Again, we can just task and see what happens. And via the mouse sniffer, we can then enumerate exactly what this second byte does. So we can see on the slide this is essentially a subcommand for the mouse command. And it will do things like tell the mouse to either left click, double click, right click, click and drag. Again, this is a rather neat capability for a piece of malware to have because it allows a remote adversary to actually interact with UI elements on an infected host. So again, watch closely. What we're going to do is we're going to task the malware to tell the security prompt to go away. Okay, that's a little more exciting. All right, so the final command I'm going to talk about is command number 16 and 17. Again, triage the command to understand the protocol. We see it invokes J with a 1, meaning it wants our command and control server to send 1 additional byte. And then invokes V, which again we know drops and executes that embedded Mach-O binary. And the process monitor and file monitor shows that happening. Most interestingly though, the keyboard sniffer lights up. For example, if we send command number 16 and a value of 65 for the second byte, we can see that the keyboard sniffer shows a key down event for the letter A. And then if we send a command number 17, it generates a key up value for that same letter. So now we have the ability to remotely interact with the keyboard or type on an infected host. So again, watch closely. We can now task the malware and write things on the screen. So for example, we can say, hi. So I repeated this process for all commands, and what this allowed me to do is understand comprehensively the capabilities of the malware, just via tasking. You know, people always say communication is key. This obviously applies to human beings, so I've been told, but here it also applies to malware as well. So we talked about some of the most interesting commands, but a few others of note. The malware supports the ability to execute system commands, shell commands, list processes, upload files, execute files. And one that's incredibly interesting, at least to me, is that you can set an alert that the malware will tell the attacker when the user is interactive or actually using the computer. Obviously, this malware is designed for interactive operations, and if you're doing interactive operations on an infected host, moving the mouse, perhaps turning on the webcam, you don't want to be doing that stuff when the user is there, because those things have very clear visual indicators, which would obviously give away the fact that the malware was on the system. That would be really bad OPSEC. All right, so now we have a fully compatible custom command and control server. So let's go hunt some flies. Now, if you ping the primary command and control servers, they're all offline. They resolve to 127.0.0.1. But if you recall, we decrypted some backup command and control servers. And guess what? They were available for registration. I was stoked. So what I did was I registered the URLs and configured the DNS to point to my custom command and control server. And immediately, a ton of infected FruitFly victims or hosts connected to me. And recall, for each connection, we get a username, a computer name, that coupled with the IP address can provide us a very easy way to identify the victims. So for example, if I was infected, you would see an IP address in Hawaii. You would see the username being Patrick and the host name, which on Macs is usually a combination of your first and last name, being Patrick Wardle. So then you could hop on LinkedIn or Google Patrick Wardle Hawaii, and you would very easily be able to identify me as a victim of this malware. Now, I'm confident to say that this malware is not designed by nation states or state-sponsored hackers based on the victims. Again, I could see who the victims were. The majority turned out to be in the United States, 90% plus. And once I kind of looked at the victims based on their names and IP addresses, they appear to be normal, everyday people. Again, these are not the type of people that nation-state malware targets. These people are normally targeted by financially motivated cybercrime malware. However, such malware generally has features to make money. A keylogger to capture credit cards, perhaps hijacking a search page, injecting ads, ransoming files. This malware had none of that. So unfortunately, this leaves pretty much a third option, was that this malware was designed by a hacker or single adversary whose goal was to basically spy on individual people or families. So really kind of creepy. So I handed off the addresses of the command and control servers to law enforcement, as well as the technical analysis of the malware and the victim list. Good news is they are now involved. And that's about all I can say about that. So let's start wrapping it up. Today, we illustrated how to fully analyze a fairly complex piece of malware just by asking the right questions. Again, in 3 steps, we built a custom command and control server, we tasked the malware, and then we observed the malware's response to reveal its capabilities. Along the way, we had to write some neat Mac OS monitoring tools. These will be made available online, fully open sourced. And the end result was a full analysis of Mac OS FruitFly variant B. We were also able to uncover a vast number of victims and collaborate with law enforcement. Of course, we could have hijacked the victims as well because we had capabilities to talk to the malware, but I probably wouldn't be here talking about it if I had done that. So people always ask me, how can you protect against these insidious threats or Mac malware in general? Obviously, it's best to perform best security practices, run a patched, fully updated operating system, but I also think it's important to run third-party security tools. So in my free time, I write free Mac security tools, first and foremost to protect my own Mac, kind of selfish, but then also make them freely available online. So I run a small Mac security website called objectivec.com. Some of the tools that could have thwarted this malware: block monitors for persistence attempts. So if this malware used an installer to persist, it would have detected it. Lulu is an open source free Mac OS firewall I'm demoing tomorrow at Black Hat Arsenal. And it could obviously detect when the malware goes to beacon out. Knock Knock is like auto runs for Mac. It will show you all persistently installed items on your system. And here you can see it's flagging the malware because it's unsigned, and also VirusTotal has some signatures for it. And then Oversight is a unique utility that I wrote that monitors your webcam and mic. So even if an attacker has infected your system and can turn on your webcam when you're away from your computer, for example, in your bedroom when walking around in your underwear or less, when you come back to your computer, there'll be a big pop-up saying, you know, process X basically just turned on the webcam. It's a good way to uncover such insidious malware. Okay, so that's a wrap. Again, thank you for attending my talk. If you're a freelance hacker researcher, check out synac.com. We're also hiring, so if this kind of stuff is interesting and you want to come work in Hawaii with me hacking on this stuff, shoot me my resume or check out synac.com. So I think we have about a minute or two, so if there's any questions, I'll take those now. I'll also be around after the talk if you want to chat as well.